Hello, welcome to Engineering Mechanics. Today we'll be looking at rigid body dynamics, looking at plane kinematics, absolute motion, and relative velocity. So on the plane kinematics, we'll be looking at just the absolute motion and relative velocity. Let's review what we did in the last class. We introduced dynamics of rigid bodies and explained the rigid body assumptions, and we also then explain the different plane motion, which includes the translation motion, the rotation about a fixed axis, and then we have the general plane motion, which is a combination of translation and rotation motion. We also explain the governing equations used in problem solving, and then we solve sample problem 5.1 from your textbook. Well, in this class, the objective is that by the end of this class, you should be able to apply the absolute motion analysis to describe the plane kinematics of rigid bodies. You should be able to use the principle of relative motion to solve plane kinematics of rigid bodies. That's the objective for this lecture. Let's start with absolute motion analysis. And this is purely descriptive, and then the example will then show you how this is applied. So first, in absolute motion analysis, we have to use the geometrical relationship of the configuration of the body. And then once we're able to get the geometrical relationship in terms of distances and displacement, then we take the time derivative of the defining geometrical relationships. This will lead us to getting our velocities and acceleration. Of course, if you differentiate the displacement once, you get the velocity. If you differentiate twice, you get your acceleration. From there, we then take note of the fact that the kinematics of particles, the absolute motion method was applied in constrained motion of connected particles, where we have connected constrained particles, and we were able to find out the length of the connections, and based on the length of the connections, we were able to arrive at our velocity and acceleration. But note that during in the particles kinematics, we only were able to deal with linear quantities and linear motion. In rigid body dynamics, however, we will be dealing with both linear and angular motions because the two are involved. Now, you have to also be consistent with your mathematics when it comes to rigid body, because it is sense sensitive, which means you must be able to specify, for example, if a moving line in the plane is specified by a counterclockwise angle theta measured from a reference axis, then this becomes your positive sense. Which means that your velocity and acceleration will be positive in the counterclockwise direction. So we have to be very careful with our sense when we are dealing with these issues. Let's look at the guiding equations. Again, the guiding equations for translation, we have the velocity, which is the derivative of the distance, and then the derivative of the velocity gives you acceleration. And then you have the relationship between, using these two equations, you can arrive at the relationship of V dV is equals to A ds. So these are the relationship for the translational. And then for the rotation, we have omega, which is your angular velocity, is the differential or time derivative of your displacement, angular displacement theta. And if you differentiate your angular velocity, you get your alpha, which is your angular acceleration. Again, from these two equations, we can arrive at this relationship, omega d omega, which is equals to alpha d theta. All right, so if we then look at the geometrical configuration of the rigid body, if it is not complex, then your analysis is fairly straightforward. You apply the equations of the linear if it's linear. But if the geometric configuration is complex, then you may need to apply the relative motion analysis. We will see how this is done as we go further in this lecture. Now you can pause your video at this point and go through the sample problems 5.4 and 5.5, and this will help consolidate what I've just explained to you with respect to the um, motion of absolute motion. So this is very important for you to just get the concept through by going through these sample examples. Okay, welcome back from listening to the sample examples. We now look at relative velocity analysis. Um, so in relative velocity analysis, if you remember in kinematics of particle dynamics, we developed and they applied this equation using two particles, A and B, that are moving relative to one another. And this will be the velocity for the particle A in vector form will be the vector velocity of the particle B plus the velocity of the particle A with respect to B, where you have to choose your reference axis, of course. And then we now apply this same principle in the rigid body. We see how this is applied in rigid body. So if you consider these 2 points, A and B, so we have A and B on a rigid body, and because this is one whole body, you can see that your R is the distance between the two bodies. And if this line AB moves from AB to its final position A prime, B prime, let's say during the time del t, we will want to find the velocity of this, maybe of B, velocity of B. And to do that, we have to look at this motion and we have to break it into 2 steps. The first step is the line moves from AB to A double prime B prime. That gives us the displacement del RB, which is this displacement. So it moves to this point, and then at this point B prime was now fixed and A double prime moved to A prime through an angle del theta. This other displacement is RA with respect to B. So that is the displacement of your acceleration, of your A double prime or A with respect to B. So you can see that these displacements must come into play. The total movement of the line AB to A prime B prime is indicated by this vector, and it's a combination of this vector, the vector RA subscript B and the vector del RB. So if A is held fixed, B will also move in a circular motion about A. So the very important point to note is that in rigid body dynamics, once you start considering one point with respect to another point within the rigid body, the movement of the moving point with respect to the fixed point will always be in a circular form. So the sense of the rotation, you can see the sense of the rotation here is counterclockwise. So if we then also hold down here A rather, and you move B, it will still also be in counterclockwise direction. So this is motion relative to A, of B relative to A, where this is the motion of A relative to B. Just one point I need to make here: if you look at R subscript B, or B relative to A, is actually negative del R of A relative to B. You can see this is going downwards, that is going that direction, but both are also going in the counterclockwise direction. So the relative velocity due to rotation, with B as the reference point from the figure, the total displacement of A will then be del A, R of A is equals to R of B, which is this vector, plus the vector RA with respect to B, where this vector will have the magnitude R theta. Now you can see that B was fixed and A double prime moved through the distance R A with respect to B, which is this distance is R, it goes through an angle del theta, so this magnitude will be R del theta, as del theta tends to 0, which means the angle of movement is small. The relative linear motion, which is R A subscript B, A with respect to B, is accompanied with the absolute angular motion del theta, as we can also observe from the translating axis. So this is your translating axis, and you can see R moves through del theta. Yeah. Okay. So the relative velocity due to rotation, dividing the equation that we have just developed, which is this equation here. So if we differentiate this with respect to the time that it took the line AB to arrive A prime B prime, that will then give us the velocity of A, which is equals to the velocity of B plus the velocity of A with respect to B, and this is equation 5.4. And then the magnitude of the relative velocity is then given as the velocity of V A with respect to B is equals to limit as del t tends to 0. You take the absolute value of this vector and divide it by del t, which is limit as del t tends to 0, R del theta over del t. And we know what this is. This is omega. So that gives us R omega. And this is the relative velocity due to rotation. If we use, let's say, I prime to represent the vector, so we drop the subscript, then we can represent the relative velocity as V, the relative velocity of V of A with respect to B will be equals to the vector omega cross product with R. And this will be equation 5.5, where omega vector is the angular velocity vector normal to the plane of the motion in the sense determined by the right angle rule. Again, just to say that the right angle rule is well explained in Appendix C, I think, in your textbook, and you do yourself a lot of good to just go and reverse and do a revision of the right hand rule. So if you look at this vector A to B, let's say in this figure we have B fixed and A moves to A prime. This is the vector, the root of the vector it will develop. And here we have A fixed and B moves in this direction, and you can see this is the vector as B moves from B to B prime. Now the point we are making here is that the relative line velocity is always perpendicular to the line joining the 2 points in question. So this is perpendicular to the line joining the 2 points. The same thing here, this is perpendicular to the line joining the 2 points. Now let's look at the interpretation of the relative equation. So this is the relative velocity equation, which is VA is equals to VB plus VA with respect to B. So if you look at this, it is given in this sense. So we want to find VA. So this is equals to, this is VB, which is this movement where the line AB moved upward by VB plus the rotational movement when B was fixed and A was allowed to move. And if you draw the vector, form, you can see that these are the vectors given here, and you can then find your VA. So it is equals to the linear motion that it went from A to A prime, B to B prime, plus the angular motion of A when B was kept fixed. And then we said that the magnitude V of the velocity, relative velocity A with respect to B will be equals to R omega, where the absolute value of omega is actually your theta dot, so the angle through which, the differential of the angle through which it moved, the absolute angular velocity of AB. So this is absolute angular velocity of AB. All right, at this point you can then also go through sample problems 5.8 and 5.9. In the videos I explain this. Going through these examples also help you to get a better understanding of the lecture. Thank you very much, and please stay safe.